Welcome to session 4 of electronic structure theory. In this session, what we'll be talking about is sort of going back to the Hartree-Fock approximation now that we've introduced the concept of what it is, and we'll talk a little bit more about getting practical about how do you do Hartree-Fock calculations. And to do the Hartree-Fock calculations, what you have to do is to express the molecular orbitals in terms of linear combinations of atomic orbitals. And these atomic orbitals are what we call basis functions. And the basis functions have certain characteristics. And there's what are called Slater basis functions and Gaussian-type basis functions that have different strengths and weaknesses. We'll talk about those things. So in session 4, primarily we'll be talking about is basis functions are used to get molecular orbitals by the LCAO-MO, linear combination of atomic orbital, to form molecular orbital process. We'll be talking about how one really plugs all this into the Hartree-Fock procedure, how it gives rise to a matrix eigenvalue problem whose difficulty in solving it scales as the cube of the number of basis functions in the calculation. And out of that Hartree-Fock procedure will come some orbital energies that we know from the preceding session, or the two sessions ago, has something to do via Koopman's theorem with ionization potentials. And out of the Hartree-Fock procedure also comes these so-called LCAO-MO coefficients that allow us to depict or to draw or to render the molecular orbitals visually. So that's what we'll talk about in session 4. This is session 4 of the electronic structure theory endeavor. And today, in this session, I want to talk a little bit more specifically about how one goes about calculating some of these configuration interaction, the CI coefficients, and also how one determines usually at the Hartree-Fock level these molecular orbitals. And the orbitals, the Hartree-Fock differential equation, that minus a half, now we're in atomic units, del squared, and then minus the electron nuclear attraction and the electron repulsion being represented with these Coulomb minus exchange things. Yeah, that's a differential equation. So you might imagine that people can solve that thing on a grid in r and theta and phi or x, y, z space. But that's not what's most commonly done. What's most commonly done is to expand the molecular orbitals. Here I represent the phi j as the MO, molecular orbital. And usually what's done is to expand it as a linear combination of coefficients called LCAO-MO coefficients, linear combination of atomic orbital to give molecular orbital coefficients, times what are called atomic orbitals, or really they're what we call basis functions. So this is some of what we have to talk about today. So anyway, the basic idea in doing this kind of LCAO-MO expansion is to make the second order differential equation, that's the Hartree-Fock equations, H times phi j equals epsilon j phi j, to make that into a matrix problem instead, just because computer programs are really good at solving matrix eigenvalue problems. So by taking this phi j expansion here, this expansion in LCAO, and plugging it into, at the bottom here you can think of this as HE, that's the electronic Hartree-Fock Hamiltonian. So HE times phi j equals epsilon j phi j. What I've done to get this bottom equation is essentially put this expression for phi j into H phi j equal epsilon j phi j. And then on the left-hand side, I've multiplied through by chi nu, the nth basis function. Now, we'll talk more in this session about what are these basis functions, but for right now, just treat them as independent functions that are, atomic orbitals that you know about, but we'll talk about them in more detail. So I've multiplied through that equation on the left-hand side by chi nu, and I've integrated over the electronic coordinate. So I end up with this expression that has this nu muth element of the so-called Fock operator, or Hartree-Fock Hamiltonian, times the C coefficients here equals the orbital energy epsilon j, and then this integral here, this chi nu chi mu, we call the overlap integral between basis functions nu and mu. So this is the matrix eigenvalue problem. The unknowns are the orbital energies epsilon j's, and the other unknowns are these C coefficients. The basis functions, chi nu and chi mu, are supposed to be known to you ahead of time. They're the functions in terms of which you've chosen to express these molecular orbitals. Now, let's just get a little bit more specific. What are these matrix elements, the Hartree-Fock Hamiltonian matrix elements, nu and mu? Well, what they are, when you write them out in detail, is they are the integral of chi nu with chi mu, and then in the middle you have your kinetic energy operator for the electrons. You could write that as minus a half del squared if you wanted atomic units. You have the electrons being attracted to each nucleus. So here's charge of nucleus A, distance of the electron to nucleus A. And then you have these terms that arise from the Coulomb and exchange integrals. And they're a little bit complicated, so I want to talk a little bit more about them. In them, you can see here there's a chi nu and there's a chi mu, but there's also this chi eta and chi gamma. Where the heck did they come from? Well, in the Coulomb integral, there also was this phi k, and what's happened is here we've written the phi k as the summation over nu of ck nu chi nu, and we've written the phi k that would appear here as the summation over gamma of ck gamma chi gamma. So the Coulomb and exchange things have also been written in terms of basis functions times LCAO-MO coefficients. And the overlap integrals are pretty easy. But this so-called Fock matrix element is sometimes called F in some text. Sometimes it's just called H little e, like this electronic Fock Hamiltonian like I've written here. They're essentially the same thing. Now I just want to discuss a little bit about some of the misery that's in these equations. The integrals that appear up here, these are called kinetic energy integrals, nuclear attraction integrals, and these are called two-electron integrals, the chi nu, chi eta, chi mu, chi gamma. And because you can see that they have four indices on them, nu, eta, mu, and gamma, there's a whole bunch of them. I mean, for example, suppose that you had m basis functions, these chi's, then there would be of the order of m squared of these one-electron integrals, the kinetic and nuclear attraction integrals, but there would be of the order of m to the fourth, because each of these indices, nu, eta, mu, and gamma, can take on m values. So there's of the order of m to the fourth. So if you had 100 basis functions, there would be 100 to the fourth of these so-called two-electron integrals. And that's one of the biggest numerical problems that we face in this kind of Hartree-Fock calculations, is that the difficulty in doing our work tends to scale as the fourth power of the number of functions that we use in our calculation. And the number of basis functions that here I'm calling m, we say that's the basis set size. Now another thing is if we go back to the equation that's the Hartree-Fock equation, this matrix eigenvalue equation here is of dimension m by m. See, nu and mu here run over m. So this is an m by m matrix. And to find the eigenvalues of an m by m matrix, this is something that you should sort of have stored in your brain. If you have a matrix of dimension x, generally it takes of the order of x cubed numerical operations to find all the eigenvalues and eigenvectors of that matrix. So the trouble with finding the eigenvalues of a matrix whose dimension is m by m is you're going to need of the order of m cubed operations to find these Hartree-Fock orbital energies and eigenvalues. But the m to the fourth that's in the two-electron integral numbers is actually more dominant in numerical difficulty and time consumingness, and also in storage. Sometimes you have to find place on a disk or in memory to store all these m to the fourth integrals. Now one other thing I'd like to just have you notice about up in here is in this Hartree-Fock expression for the Fock operator, there's a summation over k equal occupied orbitals. And then you have the coefficients of the orbital k in basis function eta, coefficient orbital k, basis function gamma. So that means to form this Fock matrix in the first place, number one, you have to know these MO coefficients. You say, wait a minute, because this equation back here that was the Hartree-Fock equation was to determine the MO coefficients. So to form the elements of this matrix, you have to already know the coefficients. Well, this gives rise to what we call the self-consistent field procedure, where we have to make some guess of these coefficients. I'll be talking about this. We take a guess and we plug them in here, and we can form this Fock matrix. Then we can go back and solve that Hartree-Fock eigenvalue thing for new values of these coefficients, plug the new values in here, form a new Hartree-Fock matrix, find its eigenvalues and eigenvectors, and so forth. And this sort of iterative process has to be followed through. But one of the things I want to stress here is that suppose you had a molecule that had, say, 10 electrons, and you were interested in the ground state configuration where you put you fill 5 orbitals with 2 electrons each. And suppose you had 100 basis functions in your problem. then this matrix would be 100 by 100. But there would only be 5 occupied orbitals. So in here you would have to be plugging in the MO coefficients for the 5 occupied orbitals. But out of this 100 by 100 matrix eigenvalue problem would come 100 molecular orbital energies and 100 molecular orbital coefficients, the coefficients for 100 separate molecular orbitals, 5 of which would be occupied, 95 of which would be what we call our virtual or unoccupied things. So in the Fock matrix, the thing that's important to sort of stress is that into the Fock matrix goes knowledge only about the orbitals that are occupied. And this is where you, the scientist, has to make some choice. When you do a Hartree-Fock problem, if you're interested in studying, say, the ground state of that particular 10-electron system, you will plug in here as these occupied coefficients, the coefficients of the 5 lowest molecular orbitals. But if instead you were wanting to do an excited state where you had the 4 lowest orbitals doubly occupied, the 5th one singly occupied, and maybe the 8th one singly occupied, then these coefficients here, these CKs, would have to be for the 4 lowest and for the 5th and for the 8th. So you would plug in different values here for these coefficients, therefore get a different Fock matrix, and you would do that kind of calculation for the excited state. Okay, now this is reiterated here where I'm talking about. Here again is the Fock matrix. It's an M by M matrix. It's written out in all these terms. And one of the points that I want to hammer home, and so I say it again, is that one needs to know the MO coefficients for the occupied molecular orbitals that go into there, these CK etas and CK gammas. And of course, as I tried to say a little while ago, this has to be done in the so-called self-consistent field iterative process to address this difficulty, where you already have to know the coefficients to form the matrix, and the matrix eigenvectors are the coefficients. So you solve that iteratively. So typically what you do in an SCF process is you guess some values for these MO coefficients, these LCAO-MO coefficients. Now most computer programs have sort of default ways of making these guesses. So let me just talk about that a little bit. One thing that programs sometimes do is they actually take the kinetic energy and the electron nuclear attraction and they totally ignore all the Coulomb and exchange interactions, because that's where in the Hartree-Fock Hamiltonian it's only in those Coulomb and exchange things that knowledge of the MO coefficients occur. So what they sometimes do is to totally ignore these Coulomb and exchange things, take only the kinetic and nuclear attraction terms in the Fock operator, and first take that as the Fock operator and form the Fock matrix using only that, and then get MO coefficients as the eigenvectors of that. And you say, that's horrible because that doesn't have any electron-electron repulsion in it. It is physically horrible. But the good thing about it is that that Hamiltonian, that's the kinetic energy and the nuclear attraction Hamiltonian, that has knowledge of where the nuclei are sitting, and therefore it has the right symmetry. So the orbitals that come out of there at least have the right symmetry. They will be of A1 and A2 and B1 and B2 if you have a C2V point group. The bad thing is, though, because they have no electron-electron repulsion, they tend to be all extremely tight orbitals, because essentially they all get sucked into the nuclei by the nuclear attraction, and they don't have any repulsion that pushes them out to become valence orbitals. So they're very bad radially, but at least they have the right symmetry. So some programs do that. Other programs will use some kind of a semi-empirical Hamiltonian that has some simple model for the electron-electron repulsions, like a Huckel Hamiltonian or something like that, to start and make an initial guess for these MO coefficients. Now usually when you do a calculation, though, if you have a new molecule and you have no knowledge, you might at some initial geometry do such a default calculation of the MO coefficients just to get the SCF process going. But the smartest thing that we almost always do is if you've done a calculation at one geometry and now you need to do a calculation in a neighboring geometry, you use the MO coefficients that already have been converged from the first geometry as your initial guess for the MO coefficients for the new geometry. You use the checkpoint file, as we call it. So that's the best thing that's usually done, is to make some guess from a neighboring geometry. So then what you do, just to make the long story short, is you make a guess for these coefficients. You plug them in for the occupied orbitals, and you decide what's occupied, which state you want to study. You plug them in, you form this Fock matrix, you then get the eigenvectors and eigenvalues of the Fock matrix, take those eigenvectors as your new guesses for the MO coefficients, being careful again to make sure you occupy the orbitals that you want to have occupied. 5 lowest or 4 lowest and then 5th and 8th, depending on what you want to do. You plug those in all the time and you keep iteratively going through this process until the values of the MO coefficients that come out on, say, the 87th iteration are the same as those you plugged in the 86th iteration to within some precision that you decide. Then you say, I've reached self-consistency. So this is the so-called self-consistent field process. And just one more time, I want to say it's important to understand that by guessing the initial values of these MO coefficients, that's where you've specified which electronic state you want to converge to. You're trying at least to converge to. And again, I'm saying that these MO coefficients that you plug in, these CK mu's, they are the MO coefficients only of the occupied orbitals. But of course, out of the big eigenvalue problem occur many orbital energies and MO coefficients, not just for the occupied, but also the unoccupied or empty or virtual orbitals. Now, sometimes you have the problem where you don't know which of these excited orbitals you want to place the electron into. Like in that hypothetical molecule I was talking about, if you don't want that ground state, if you want, say, maybe a pi to pi star excited state, you have to first of all look in your occupied orbitals and see where is the pi orbital out of which you want to take an electron. But you got to look up in the virtual orbitals and find out where is a virtual orbital that looks like pi star. And it may not be the LUMO. It might not be the orbital that's the first one up. So let me just give an example here. Here I'm depicting a bunch of orbitals, and all that's important is these are some orbitals for the formamide molecule. So we have a carbonyl group with an NH2 group next to it, and then a hydrogen on the carbon. And I just want to sort of show you some of the orbitals here. The highest occupied MO, see it down here in the right-hand corner, the HOMO, is a pi-type orbital on the sort of oxygen-carbon-nitrogen moiety. The HOMO -1 is actually a lone pair orbital. The HOMO -2 is another pi orbital. You know, in the OCN world, you have a delocalized pi bonding orbital, and you have a sort of a non-bonding orbital too. If you think instead of you have a carbonyl pi bond, and then you have a lone pair on the nitrogen, but that lone pair really gets involved in the pi framework. And so the HOMO -2 and the HOMO are essentially this CO pi bond and the nitrogen lone pair really combined into a delocalized 3-center bonding orbital, HOMO -2, and then a more localized orbital, the HOMO. Now that's not too surprising, but when you do a Hartree-Fock calculation, and here I've talked about a specific basis set that was used, we'll learn it later in this session what that notation means. Actually in the next session we'll learn about that. But the main thing I want to show you is that and this happens to be a pretty decent basis set that people would not be embarrassed about using. But if you say I want to study the pi to pi star excited state of this formamide, and you take an electron, say, and you pull it out of that HOMO, well that's okay because that is a pi orbital. But the LUMO, the lowest the first virtual orbital, looks like this. It's sort of an orbital that's out in space. Now this molecule is a fairly polar molecule, so it has some states that are sort of like dipole bound states. They're states where the electron is trying to be bound to the electrostatic potential of the molecule, not in a valence orbital. So LUMO +1 and LUMO +2 are not even valence orbitals. They're just orbitals out in space that are there because your basis set was pretty big and it's trying to attract an electron to the periphery of the molecule. The orbital that is the LUMO +3 is actually the orbital into which you would want to be placing your electron if you wanted a valence excited pi orbital. So you have to visually often look, that's what I'm trying to teach here, is that often there are a bunch of these virtual orbitals that are sort of in the way, and you have to identify visually by looking at the orbitals which is the orbital you're really after. And so if you were interested in the pi star state of formamide, what you would be doing is to do a calculation where you put one electron in the HOMO and one electron, say, in this LUMO +3 as your initial guess for the pi star state. Okay, now I just want to remind you something too about when we do unrestricted Hartree-Fock calculations. Now, what's different about them and why are they not eigenfunctions of S squared and all that? So suppose you have an open shell situation. And for example, it might be, as I've indicated in this slide here, it might be this 1s squared, 2s squared, 2px alpha, 2py alpha carbon atom. That's an open shell. It has more alpha electrons than it has beta electrons. The way the Hartree-Fock procedure goes there is you form a Fock matrix for the alpha world and a Fock matrix for the beta world. And out of the Fock matrix for the alpha world, you will get the MO coefficients and orbital energies appropriate for the alpha orbitals. And out of the beta matrix, you'll get orbital energies and MO coefficients for the beta orbitals. But let's just pretend for a minute you're forming the alpha Fock matrix. So you're pretending that this chi nu and chi mu relate to alpha spin orbitals phi's. Well, the main difference, the main thing where the spin comes in is in the kinetic energy and nuclear attraction. There's nothing that's spin dependent there. But down here where you summation over k, see, the sum over k is a sum over all occupied spin orbitals. So, for example, this k will be 1s alpha, 1s beta, 2s alpha, 2s beta, 2px alpha, and 2py alpha. So, in the two-electron integral here, let's just consider this Coulomb integral. This chi nu and chi mu, they are by assumption alpha, because we're forming the alpha block of this Fock matrix. So if chi nu and chi mu are alpha, then chi eta and chi gamma, they can be alpha or they could be beta, and the spin won't kill this integral. But in the exchange integral, what's different is, see, here we have chi nu, which is alpha. Over here we have chi mu for r prime, and that's alpha. So this chi eta here has to be only alpha spin, or it will integrate against that chi mu and kill it. And likewise, chi gamma has to be alpha spin, or it will integrate against this chi nu and kill it. So in the exchange terms, only those things where eta and gamma are alpha, and therefore they came from a spin orbital k that was alpha, only they will contribute. So just to make the long story short here, let me just try to show you how this game would go. What I'm saying is that in this list of integrals, in forming the Fock matrix, if mu and nu are alpha, then in this summation over k, only 1s alpha, 2s alpha, 2px alpha, and 2py alpha would contribute to this exchange term. In contrast, when we form the beta block of this Fock matrix, where nu and mu are beta now, spin orbitals, so we're trying to form a different matrix for the beta world. In that world, k, the summation over k here would only be 1s beta and 2s beta. It would not have any 2px or 2py at all in its exchange part. So the actual values of the numbers that would enter into the Fock matrix for the alpha and beta world would be different. As a result, the Fock matrices for the alpha and beta world are different. As a result, the orbital energies that come out as eigenvalues of those matrices and the MO coefficients on each cycle of the iterative process that come out will be different. So you'll get different orbitals for the alpha and beta world. And here's just an example of, if we take the F-Li molecule, sort of like F minus Li plus, it's ionic, and we add an extra electron to it to make it an open shell, it forms one of these so-called dipole bound-like states. So here we have the F center, and buried underneath here is a lithium plus center. And this orbital on the left is the alpha orbital, the singly occupied molecular orbital that is of this dipole bound looking shape, and it has this orbital energy. It's bound by 0.01219 Hartrees, number 27.21 EVs. The beta orbital that goes with this alpha orbital is different than it, and here it is. You can see physically it's a little bit more radially extended. It sort of looks roughly the same, but it's not the same, and it has a different orbital energy. So when you're doing these unrestricted Hartree-Focks, you always have a ladder of molecular orbitals that are alphas and betas, and one of the things to always be careful about is that if you go orbital 1 beta, sorry, I think I just turned off my screen there, and then orbital 2 alpha, orbital 2 beta, orbital 3 alpha, orbital 3 beta, you would tend to think that orbital 7 alpha and orbital 8 beta will be pretty close to one another in physical appearance, but that may not be the case. There are differences, and sometimes these differences can actually give rise to slight variations in orbital 7 alpha might look more like orbital 8 beta or orbital 6 beta. So when you're doing UHF calculations, often you have to be careful as to which orbitals you think are which by looking at them. You just can't count, and assume that the 7th one here is the partner of the 7th one there. They actually may look quite a bit different from one another. In this example, they're not much different. Okay, now let's go back to this. In the Hartree-Fock thing, we said each molecular orbital was a linear combination of MO coefficients, LCAO-MO coefficients, times basis functions. What are these basis functions? Well, and I've said this to you a few lectures ago, but I just want to be more detailed now. In the early days, what are called Slater-type basis functions, Slater-type orbitals, which have the form of a normalization constant, a spherical harmonic, S or P or D or F or whatever, and then the radial part of the Slater basis functions was of the form r to the n minus 1, n's the principal quantum number, so like a 1s orbital would have r to the 0th, e to the minus some zeta r. Zeta is the so-called orbital exponent. That will depend upon the nuclear charge. So for example, for a carbon nucleus, it will have a larger zeta than for a beryllium nucleus, because the nuclear charge of carbon is 6 and beryllium is 4, and this exponential fall off in the e to the minus zeta r will be sharper for carbon, so carbon will have a bigger zeta basically. So the quantum numbers that characterize Slater-type orbitals are n, the principal quantum number, and L and M that describe the spherical harmonic, the shape. And then there's an orbital exponent zeta that describes that controls the radial size of these orbitals. In what are called Cartesian Gaussian-type orbitals, that are the most common things that we use, we have the basis functions expressed as a normalization constant. The radial part is e to the minus alpha r squared. We use alpha usually as the orbital exponent notation for Gaussians, but it's r squared, so it's this. Remember, Slaters have this cusp behavior. Gaussians are flat-topped because they have this zero slope at r equals 0. And then, instead of expressing the angular dependence of Gaussian orbitals in terms of spherical harmonics, it's more common in these so-called Cartesian Gaussians to just say x to some power, y to some power, z to some power. For example, if we want an S-shaped Gaussian orbital, we would say A equals B equals C equals 0. That's x to the 0th, y to the 0th, z to the 0th, e to the minus alpha r squared. That's spherical. If we want a px orbital, we will say x to the first, so A is 1, B is 0, C is 0. If we want a pz orbital, we'd say A is 0, B is 0, C is 1. So that's how we choose how to describe the angular dependence of these Cartesian Gaussian orbitals. Now, I mentioned this some time ago. We're going to iterate it again. Slater-type orbitals, one of the nice things about them is they can have this proper cusp behavior at the nucleus. Gaussian orbitals are flat at the nucleus. They have zero slope. So you say, let's use Slater orbitals. The problem is these two-electron integrals that we face down here at the bottom, these integrals that arose in the Fock matrix element that have 4 indices on them, you just can't do them if you use Slater basis functions as these chi's. There's if these chi's are sitting on 4 separate atomic centers. See, each of those basis functions, when we say the word r here, or r squared here, or x or y, those coordinates are referred to the center, the nuclear center, where this basis function is located. And the basis functions generally are located on the atomic nuclei. So these integrals that arise here in the Hartree-Fock theory, the 2-electron integrals that are m to the 4th of them, they can in principle involve basis functions centered on at most 4 different atomic centers. And you just can't do the integrals if nobody's written down an analytical expression for the integrals that you can code up on the computer. Whereas for Gaussian basis functions, the integrals can be coded up very efficiently and have been. So that's the primary reason that we use Gaussian basis functions. Well, what do we do then about this doggone cusp behavior that Julio Fichelli in particular with NMR might be interested in being worried about? Well, typically what's done is to realize that the Gaussian basis functions are all flat-topped. They don't have this cusp behavior. The thing that has the cusp behavior is this red function here. So sometimes what people do is they will take a series of, say, a looser, a medium, and a real tight Gaussian function and try to take some combination of the loose, the medium, and the tight. It's called contracting the Gaussians. Contracting means that you're going to take a combination. Now the combination you take is not these LCAO-MO coefficients. They're things you get from the Hartree-Fock procedure. But what's sometimes done is we say, rather than just use these chi's as being primitive, that it means just the kind of Gaussians I showed you before, primitive Gaussian functions, people say, let's take these chi's and define them to be some combination of a loose, a medium, and a tighter Gaussian function, and try to adjust those combination coefficients to make the function look as much as possible like that red one. Now the problem is, you know, in principle, it's impossible, because every one of these blue ones is flat-topped, and the red one ain't flat-topped. So you can't really do this in principle. But you can try to get at least fairly close to the nucleus a combination of these three blues to look like the red. And that's called contracting the Gaussian functions. And people do this quite routinely. Okay, so in most atomic orbital basis sets, you know, these chi's that we're talking about, most of the time what we have is different kinds or different categories of basis functions that we use. Not different alternatives, but every basis set includes some, usually, of these kinds of functions. So most of them include some core basis functions. They tend to be these contracted Gaussians that have been added together to give them sort of, as close as you can get, a cuspy-like behavior near the nucleus, a sharpness near the nucleus. So there's usually core basis functions that are combinations or contractions of primitive Gaussians. And then there are valence basis functions. So let's say you're a carbon atom. The 1s world will tend to be described by some contracted core basis function. The 2s and 2p world will be described by what we call valence basis functions. And we'll talk a little bit pretty soon about what they are. But in addition to these functions that are describing, say, in the carbon, the 1s and 2s and 2p, there's other kinds of functions whose names I want to say right now, but then I'm going to explain what these names mean. There's polarization functions. Now, polarization functions have often something to do with angular directionality. I mean, suppose you're doing a calculation on cyclopropane, and you know the bond angle in cyclopropane is 60 degrees. Well, if I've told you that you have in your basis set s orbitals and p orbitals, you sort of know from freshman chemistry that you can form sp hybrids and form a bond of 180 degrees, or sp2, 120 degrees, or sp3, 109 degrees. But how in cyclopropane can you form then bonds that are pointing at 60 degrees? You need some different angularity in your basis functions to do that. And that's one of the things that polarization functions will be doing for us. And I'll tell you what they are in a little while. Then there's diffuse functions. In the basis sets that we tend to grab off the shelf, they tend to have their radial extent chosen to be appropriate for the atoms in their low energy states. That is, the basis functions you pull out off the shelf for carbon atom are pretty good at describing carbon atom if it is in its ground state, triplet P or singlet D or singlet S that relates to its 1s squared, 2s squared, 2p squared configuration. But if you're studying some kind of a carbanion where that carbon center has now a negative charge on it, the orbital in which that electron is sitting is expected to be a little bigger than it would be in a neutral carbon atom. So we need some diffuse functions to let this orbital become bigger. They're diffuse because they're more radially extended. Now sometimes if the functions that you are wanting to study involve binding the electron to your molecule by this so-called dipole binding, or in some what are called Rydberg states that we'll show some examples of, then the orbitals have to be even larger and more diffuse. So there's like super diffuse functions that we call Rydberg functions. So let's just talk a little bit now about these core, and then valence, and then polarization, and diffuse, and so forth. In the core and valence basis sets, there's a whole hierarchy of basis functions. And generally, as you add more and more and more, you're doing a better and better description. See, because what you're doing is you're saying, my molecular orbital phi j, I want to express it as a summation over mu of Cj mu chi mu. And in principle, a mathematician would say, take that chi mu set to be complete. Well, we can't do that because that's too big a set. You know, it's infinite. So we have to work our way up to better and better and better choices of those chi mu's that are more and more and more complete. So the simplest thing that we do, that is the cheapest calculation one can do, is to do what is called using minimal basis sets. That is, you take a contracted Gaussian-type orbital and you use one for each one of the core and valence atomic orbitals in the atom. So for example, in a carbon atom, this would mean that in your basis set, there would be one chi that would be a tight, that is radially tight, compact, contracted. So it might be a combination of Gaussian functions, but it's one contracted, tight, Gaussian-type orbital of S symmetry. And you'd call it the 1s basis function. There'd be another S function that also could be a contraction of two or more Gaussian primitive functions, but it also would be a S character. It would be looser, larger radially. And then there would be one px Gaussian function, one py, and one pz. That's minimal. You say, isn't that good enough? Well, no, because these basis functions have fixed and specified orbital exponents, that is radial sizes. So you'd have to be real lucky to have chosen those orbital exponents to be proper for the carbon atom in the particular valence that you want to study it. Is it carbanion? Is it carbon neutral? Is it carbocation? So you have to have some ability to go beyond this because you want to allow your calculation to describe different radial extents in the electron distribution. And you don't want to have to rechange your basis functions every time. These basis functions are supposed to be things we pull off a shelf and we can use them anytime we do a carbon atom. And carbon atoms in different charge states can't be treated by these minimal basis sets because they're too rigid radially. And let me just give you an example of how bad or how good this kind of stuff is. In this picture here, what we're showing is in the dark black, the darker color, is the 1s, 2s, and 2p radial functions that come out of a very high quality, very large basis set calculation on the carbon atom. And then in the lighter colored things here on the top are if you use a minimal Slater-type orbital basis for the carbon atom. Now we can do it for an atom. Remember, Slaters we can't do for molecules that involve 4 and more nuclear centers. So the radial, if you use minimal, that is just one S function that's tight, one S function that's looser, and one set of px, py, and pz functions, you can do a pretty decent job of describing the real radial distribution of the electrons in the carbon atom. The Gaussian, if instead you use a minimal Gaussian basis set to do the same thing, here's the 1s, and the 2s is not looking as good as the 2s that comes from Slater, and the 2p is also qualitatively worse than it was Slater. So it means Slaters actually can do better than Gaussians. But this is just minimal Slater and minimal Gaussian, and we're never going to really do that. What do we have to do? Well, we have, instead of minimal, we have what's called double zeta, or triple zeta, or quadruple zeta basis sets. The zeta refers to, because in our mind we remember that the orbital size, the radial size, is governed by this zeta, in the case of Slater, or alpha parameters. So when we say double zeta basis set, what we do is the following. For carbon atom, we would say we would have two tight S functions. Now, how would they differ? One would be real tight, and one would be less tight. So generally, if you have a minimal basis set, a function that's of a certain tightness, in the double zeta basis set, you'll see a function that's a little bit tighter than it was in the minimal, and a little bit looser than the one that was in the minimal. You're trying to span different radial space, if you will. So we'd have two tight S functions to span the 1s world. We'd have two looser S functions to span the 2s world. So they could be appropriate for carbon atom as a carbocation, a carbon neutral, and a carbon anion, where its radial extent wants to vary. And we would have two sets, that is two px's, two py's, and two pz's as basis functions instead of just one. Of course, in triple zeta, yep, 3 tight S, 3 looser S, 3 sets of P's, and so forth. Now, the motive, you say, why are we doing this, adding more and more functions? Because we know it's going to cost us more and more computer time. But it's the desire is to provide more radial flexibility, and in a sense, to provide more flexibility in the variational process. Remember, variational process arose because the Hartree-Fock equations, H phi j equal epsilon j phi j, were derived by minimizing an energy. And that variational minimization, one of the ways we can make that energy get better and better and lower and lower and lower, is to make the space in which those basis functions, those molecular orbitals are expanded, more and more flexible, so they can get the energy lower and lower and lower. Okay, so that's why we're doing that. So what we just talked about is the core and valence type basis functions. You know, minimal, double zeta, triple zeta, yep, quadruple zeta. Sometimes people do 5 zeta, 6 zeta these days. Now, polarization functions. Polarization functions have actually several purposes, but generally what they are is they are functions of one higher angular momentum than you think of when you think of that atom's valence space. So for a carbon, nitrogen, or oxygen atom, in other words, the 2s and 2p functions are valence. A polarization function will be a d function. But one of the things that's important to hear is these functions are not at all appropriate for a carbon atom that would actually be in a state like 1s squared, 2s squared, 2p1, 3d1. That is, the polarization functions are not attempting to describe a real 3D orbital of an excited state of the carbon atom. What they are instead is they are functions that have d character, dz squared and x squared minus y squared and all that, 5 of them. But what's different than the excited orbitals of the atom, they actually have the same radial size as the valence orbitals. Now, I know you're saying, why is that the case? What is that for? Well, I have to explain with some pictures what it's for. But the general idea to keep in mind is polarization function on a carbon, nitrogen, or oxygen is going to be d. A polarization function on a hydrogen atom is p, one higher angular momentum than you think that atom deserves in its ground state. But number 2, the radial exponents, those alphas or zetas, or the size of the polarization functions, are the same as the valence orbital. So a polarization function that's a p orbital on a hydrogen basis, on a hydrogen center, is of the size of a 1s orbital. It's not the size of a 2s or a 2p orbital. It's p, but its radial size is that of a 1s. Now, here I say, okay, what the polarization functions give added angular flexibility to the LCAO-MO process, and they also allow one to put into place these so-called angular correlations. Now, those statements there, you should say, that's not clear to me, Jack. What do you mean by that? So I need to explain that. So I'm going to spend a little bit of time now explaining what it is that these angular terms in the polarization functions are really about. But in this picture, I'm just trying to show, suppose one had an atom that has sort of s orbitals and p orbitals that were of the valence space. So here I've drawn an s and then the p's. If you were to add d polarization functions, here's 5 d's, they would be radially in size similar to the s's and p's. See, they're not bigger. And if somehow you added what are called a second set of polarization functions that would be one higher angular momentum yet, f, they would not be bigger and bigger. They would still be of the same radial size. And if you were to add g polarization functions, this is almost ridiculous. People very seldom do this except for very big basis sets. They would not get bigger. They would be of the same size. The way to think about this is that when you have space, what we're trying to do with these basis functions is by going from single zeta, double zeta, triple zeta, we added radial flexibility. So we sort of span more and more of a given volume. We allowed different radial flexibility. Now what we're doing when we try to do these things by adding more and more high angular momentum functions is we're trying to make our ability to describe the different angles higher and higher and higher. So we're trying to add angular flexibility. So just to give you a hint, if we go back to that cyclopropane example, to get bonds that are directed with 60 degrees between them, you can't use s and p basis functions only. But if you combine s's and p's and d's, you can get things that point 60 degrees from one another. So that's one of the things that polarization functions do. They give you angular flexibility so you can let the electrons point in different angular directions. So even though they look complicated and you say, boy, G functions for a carbon atom? No, it's not the carbon atom having a G electron. It's you want some angular flexibility in your basis set. So one thing polarization functions do, they're about 3 things. They give angular flexibility. Another thing that they do also is they allow the electrons to undergo this dance. And I just want to remind you of the thing I asked you to commit to memory last time, that when you have 2 Slater determinants that differ by taking 2 electrons, say out of phi alpha, phi beta, promoting to phi prime alpha, phi prime beta, and you have 2 of these things combined together in a CI, configuration interaction way, you can instead think of that as a singlet coupled pair of situations where one of the two electrons is in a polarized orbital that's phi minus a little bit of phi prime. And when we talked about the alkaline earth atoms, we talked about s orbitals, like in beryllium, for example, 1s squared, 2s squared. Then the excited determinant would be 1s squared, 2p squared. So the s orbital and the p orbital, in that case, the 2s and the 2p do have radially the same size. So in that case, we wouldn't need polarization functions. So we would essentially take the 2s and 2p, they would form polarized orbital pairs, look like this. The electrons get to dance on different sides of that nucleus. But, for example, if you were doing a calculation on H minus, just a hydrogen hydride ion, if you said, well, I have 1s squared, that's my first determinant here. What I'm saying to you is if you have another determinant where you've excited those two 1s electrons up to p squared, but not 2p orbitals that are radially big, but p orbitals that are small, polarization functions. So the two determinants then would be 1s alpha, 1s beta, and then let me call it 1p alpha and 1p beta, just to mean polarization-sized p orbitals. Then in that case, the 1s orbital of the H minus and the polarization p orbital could be combined to form these left or top and bottom or in and out or left and right dancing polarized electron pairs. So polarization functions also can get used in the configuration interaction to allow the electrons in a given valence orbital to angularly dance. So they can give rise to this angular correlation as well. So bond orientations that are out of the ordinary, and then also angular dancing. Another thing, which is sort of like bond orientation, but let me just, I view it as slightly differently. It's letting the electron pairs point in slightly different directions than you might think of. Suppose you're thinking of a carbonyl bond. It could be in formaldehyde or in carbon monoxide. If we're thinking about the pi bond in, say, a carbonyl group, we have on the left here a carbon p orbital sticking up and down. On the right, we would have, of course, an oxygen orbital that I haven't drawn sticking up and down, a p orbital. If I take the carbon atom and I add a d orbital that's of the same size as the p orbital, see, here's a d orbital, it's a d pi, and it's sitting right on top of the carbon p pi. If I take and let the LCAO-MO process take a little bit of the p pi and mix in some of this d pi, I get this bent over orbital that's here on the right. It's sort of a pi orbital on the carbon, but slightly distorted that way. Likewise, on the oxygen nucleus, I can have a p orbital that's pointing up and down. If I put a polarization d function on the oxygen nucleus, that's this d orbital here, I can combine those so that they point this way a bit. So the LCAO-MO process, by having available not just the p's, but also the d's, can form pi bonds that are more, if Mother Nature's energy minimization wants them to be, that are more bent over, that aren't just these sideways overlaps that we normally think of in freshman chemistry. So letting the electrons in the valence orbitals distort to form weird bonds, 60 degrees, or to form pi bonds where the electrons go more or less where they want to minimize the energy, that's what polarization functions are about. Okay, so what do we have so far? We have core and valence functions, single zeta, double zeta, minimal, double zeta, triple zeta, blah, blah, blah. We have polarization functions. We also have, though, diffuse functions. And I want to point out there's a web page here at the Pacific Northwest Labs that has a lot of nice basis functions you can just download to do all these, to do the calculations. But in the Pacific Northwest National Labs, you'll find diffuse basis functions, for example, that you might want to use in F minus or in the oxygen center of OH minus or on the carbons and oxygens in carboxylate anions. Now those kind of what are called conventional diffuse basis functions, primarily what they are is people say, well, the basis functions that have been designed at the double, triple, zeta level, they're okay for the atoms in their neutral states and in their cationic states. And these functions just say, well, sometimes people are interested in anions, so we better provide them one more function radially to add to to be good enough for the anion. So that's what these are for. But if you have a molecule that has a very unusual orbital, and I'm just going to show you one here. Here, this is the arginine anion in its so-called zwitterionic form. It has a positive end to it, and the electron, when you form the arginine neutral and add an electron, it goes not into a nitrogen or carbon valence orbital, but into this big old diffuse blob that's on the positive end of the molecule. The electron's essentially just attracted to that positive site into a Rydberg or extremely diffuse zwitterionic orbital. That orbital there is very difficult to describe with the conventional valence and core and conventional diffuse functions that one would download from, for example, the P&L site. So there also are so-called extra-diffuse or Rydberg orbitals that people have developed that are useful for describing these cases where the electron is bound in a Rydberg orbital or a dipole-bound orbital or a zwitterionic type orbital like that. Okay, that's the end of that baby there.